Hello class, this is a continuation on proving these three ideas using axioms. Alright, so let's get straight to it. So the first one I'd like to prove is the angle sum of triangles equaling 180. The axioms that I'll be using to prove this one are axiom 6, 8, 10, and 11. Alright, so here we go. So axiom 6 shows, the wording of this is rather tricky, but I'll break it down for us. So there's two parts to axiom A. M, meaning the measure of angle BAC, is 0 if and only if, just a fancy way of saying if, BAC are collinear, meaning they are in a straight line like this. So BAC are in a collinear straight line, and A is not between B and C. So breaking it down, A, B, and C, or B, A, and C are collinear, and A is not in between B and C. The angle BAC, so BAC looks rather funny because if it were BAC, we can see this angle. But BAC goes that way. Well, that's going to equal 0. So just to contrast this, BAC be an angle, but because BAC goes back here and makes a flat line, that angle is actually just going to be 0. Part B says that if A, it's the exact same thing, but this time, if A is in between B and C, the angle BAC, well, that just makes a straight line. So it's either a straight line makes an angle of 0 or an angle of 180. That is the summary that we're trying to state here. So the summary is that angles on a straight line are either 0 degrees or 180 degrees. The most common one we accept is that it is 180 degrees. That's the first axiom we're going to use. Hope you understand that one now. We're going to use this one. So angles on a straight line are 180. Now it says, another one, suppose A, B, and C are collinear points, meaning they are on the same line. Here it is. With B between A and C. So there we go. B is between A and C. And X is not collinear, meaning the point X is just anywhere off to the side. Whoops. It can be anywhere off to the side, so long as X is not on the line. Then it says the measure of angle AXB, AXB, plus the measure of BXC, BXC, must equal AXC, AXC. In essence, this angle plus this angle must equal this angle. Moreover, meaning on top of this, ABX, so ABX, must equal XBC, must equal, so adding those two, so these two, must add up to ABC. Now, a simple way of saying this first part is that adjacent angles can add. So these two angles are adjacent, therefore they must be able to add. The second part, well, because ABC is a straight line, that's just another way to say that supplementary angles add to 180. Now, this isn't a theorem, but if we just imagine what would happen in the particular case if BX were to be 90 degrees. Well, that requires a different theorem to say that 180 chopped in half gives 90. That's a different axiom, but we won't go into that now. But if we imagine this, and just imagine now, if we, let's take this, we were to do it like this now, like so, let's say that is x. So we said that that is 90 degrees. We now just move A here, C here, and B is anywhere along this line. Now because of that, if you take a look, because we know that this is 90, and these two have to add as does this one, well then this is a proof or an axiom for complementary angles add to 90. Because that's 90 and these two follow the principles shown here in this axiom, complementary angles add to 90. But the main one I'm looking at is supplementary angles add to 180 degrees. So two axioms: angles on a straight line are 180. Angles that cut other angles can add. The last two axioms are rather straightforward. It says, given a point P and some line L, there's exactly one line through P that is parallel to L, meaning there's only one possible way for me to construct a parallel line to L. If I were to try make a different line that's parallel, it would have to be to a slight angle like this, because that's the only way I could make it not be the same line. But then this is not going to be parallel. So there's only one line that is parallel to L through this point. So that's another axiom. Another axiom that we're going to use is that if L and L prime or L dash are parallel lines and M that meets them both, alternate interior angles have equal measure, meaning these ones and these ones, as do corresponding angles. So this is actually an axiom that we have to accept in geometry. Okay, now that we know these, let's take a look at our proof for the angle sum of a triangle. So here we have a triangle ABC. Now the angles I'm just going to label as little a, little c, little b. Now at this point I'm sure we can all imagine that BC could just be a straight line. We could just imagine BC being a line like this. Okay, and let's call that line L. Just using this last axiom, using this last axiom, imagine that this is point P and that is L. There's exactly one parallel line that goes through point A. So those two lines must be parallel. Let's call that L prime. Now, as it just said here, that alternate angles have equal measure. So this angle and this angle are equal. If you can take a C and look, that is the case that we have here. That's B, therefore this must be B. Likewise, there's an alternate angle here and here. So this must be angle C. Now would you take a look? At this point, we have a straight angle. So this angle here, as according to axiom number 6, it must be 180 degrees. So this line is 180 degrees. But then axiom 8 says that adjacent angles can add. Well, these three angles are all adjacent. Therefore, these angles must add. So it must be the case that angle A plus angle B plus angle C must equal the straight line angle, which is 180 degrees. So this straight line must add up to B, A, and C. But because of the other axioms, this alternate angle and this alternate angle, these are also B, well, ABC, A plus B plus C, must equal 180 degrees. So this is a proof that the angle sum of a triangle is 180 degrees. So I hope that shows how we can use axioms to construct a proof. All right, so now that we've established this first proof, I'll see you in the next video where I further use other proofs to construct more proofs on this topic. Hope to see you then, and best of luck.